So let's start. So what I'm going to do first is to look at your comments on the exercise and try to give answers to the comments. So thank you for adding comments on the for the exercise. I guess that everyone will be happy with the information that is behind. So let me just increase the size and have a look on the different exercise. So the first comment was on combustion, and I'm going to explain you the combustion in 5 minutes. So the idea would be that I will go into more details on how combustion has to be calculated and what it implies when you are analyzing the process. So this is my first comment, so it will be in 5 minutes. The second question was the problem of having a negative answer when doing the energy balance in the deaerator, and Francesca gave an answer, in fact. The value is small, but it should not be negative, which means that you have to take care about the enthalpy differences with enough, or the flows with enough decimals. That would then give you the answer. So what is happening at the level of the deaerator, and I will switch to the other application here. So the reason why, and it's perhaps what is the most important part, so the reason why you have the deaerator here okay, so the deaerator is here, huh? And what you can see is that the deaerator is on the flow of steam. So it is part of the production of steam, and I'm going just to explain you why we have a device like the deaerator in this system. And the explanation is the following: is that when you have to produce steam, in fact, you take water, which is in the liquid form here. This water is going to be pumped in this pump and go to high pressure. So the pressure here is supposed to be 45 bar. And so the water goes in this direction here, and then is going to be vaporized and superheated in the boiler. And so here you have the vapor phase, which is at a temperature. The temperature here is higher than the saturation temperature at the pressure where we are. Okay, so it means that if I want to just make a very small drawing about what did happen here for the vapor, so you have the temperature here, you have the heat load here. So the liquid here, this part, is going to be preheated, then vaporized, then superheated by receiving heat from the combustion gases. Okay? So, and afterwards, the vapor is going to be used mainly here in a turbine, where it is going to produce mechanical power, which means that it is going down in pressure. Okay, so the pressure is now here, following still this flow here. It is going to come here at a lower pressure and has delivered here a certain amount of mechanical power. Once it is there, it is going to go from the gas state to the liquid state. So here we are the vapor state, and here we will be at the liquid state, coming back here. And what you can see is that the pressure is lower. It means that when the vapor is doing the heat exchange, typically the heat exchange area is going to fix the pressure at which the heat exchange is happening. The reason for this is that inside this heat exchanger, the heat exchanger that is here, which is heating a fluid from 4 degrees C to 80 degrees C, if I'm again plotting what is happening when I'm looking at the temperature and the heat load, I have now the vapor. I take the same color, so the vapor, which is at lower pressure, that is going to be first subcooled. Then when it will reach the saturation temperature here, it will condense, and then sometimes it is a little bit, but not too much, subcooled to reach the 110 degrees C, which is shown here, starting from a temperature that you have to calculate when you have when you are at 3 bar and you are superheated. So you can calculate this value by looking at knowing the temperature that is here, knowing the pressure that is here, and calculating the expansion. Okay, so you can calculate the enthalpy here, knowing the enthalpy here, and the enthalpy difference between these two, which is the mechanical power that is produced, and the mechanical power that is produced is calculating using the isentropic efficiency. Okay, so here the steam is going to be condensed, so this superheated, condensed, and then subcooled, and this is used in order to heat. I'm going to use another color here to heat this flow here. And this flow is the process flow that goes from a given temperature from 4 degrees C to 80 degrees C. Okay, so now the steam is, so the vapor is, or no, the water is in the liquid state, and it is going to be returned to the process. So it goes mainly in this way. It seems, however, that on the way back home, the water has been lost, and there are some losses, which are mainly losses that occurs in pipes because the pipes are cooled down, and sometimes there is venting that is there to prevent having gas traveling with the liquid. Okay, so you have some losses, and the losses have to be compensated because the water has to go back here. Okay, and the amount that is lost here is going to be compensated by adding cold water here. So at 25 degrees C. Right? So this is the water that is entering, fresh water that is entering the cycle. And this fresh water is at ambient conditions and has been demineralized by using membranes, for example, to take out all the minerals, because I don't want to have minerals accumulating in this cycle here. Okay? So now what is happening is that I'm mixing water, which is at 110 degrees C here, with water at 25. It results a certain temperature here. And the risk is that this water that is circulating will have also some inlets of gas because just the pipes are not really tight, and it might happen that at some places you have entrance of gases. And when you have liquid with gas, then you have bubbles. Okay, and when you heat a bubble, okay, at the difference of the liquid, the gas is going to expand. Okay, so PV equal nRT. So you have a certain, if you increase the temperature, the pressure is constant, then the volume is going to increase, right? And as the volume is going to increase, and the gas is much lighter than the liquid, it is going to take a lot of room in the pipe. Okay, and if you have a bubble of gas that is then taking more and more room in the pipe, it is going to try to take more place, and it will push the liquid out. Okay, and this is going to create problems in the heat exchangers and everywhere. Okay, and to avoid having the gas that would do this effect, what we do is that we are going to boil the water in the deaerator, which is here. So, and the way it is done is by, you are going to take a small amount of vapor here, you will inject in the liquid in such a way that the liquid will be just at the boiling point. When the liquid is just at the boiling point, it means that everything which has a higher tendency to go in the gas phase as compared to the water will go in the gas phase. So all the gases that will be there will go in the gas phase, and they will be deaerated. That's what we name the deaeration. It means that we are sure that if we boil the water, there will be no other form of gas in the liquid. So everything will be that is lighter than the water will go into the gas, right? And so we stop here. Typically, there is a set point in 1999 when the pressure is 1 bar or even a little bit higher, and the gases will leave the system here. Okay, and this is the reason why we have to do this deaeration. Now the deaeration is going to reach a temperature here by injecting a gas which has a high enthalpy, so the vapor, with the liquid which is here. So this is a liquid, this is the vapor phase. And as the vapor phase has a much higher enthalpy than the gas phase, okay? And if I'm looking at what this the molecules that are here will be here, you can see that those molecules will be in the liquid phase. So it means that each molecule is going to deliver some enthalpy by condensing. And this heat of condensation will be used in order to heat the liquid water. Okay? But so to give you just an order of magnitude, the heat of vaporization is of the order of magnitude of 2,200 kilojoule per kilogram. So this is the enthalpy of the gas phase delivered by the condensation. And if you want to increase the temperature by 1 degree of the water, is 4.2 kilojoule per kilogram. So you can see that 1 unit of mass of the vapor phase is delivering much more heat than the temperature, which is the energy that is needed to raise for 1 degree C. Okay, and therefore, typically the flow here will be very small. Okay, but in reality, it's a loss. Okay, it would be better to not have to inject this flow here, because then it's a flow that does not pass through the turbine. Okay, so now you have the explanation about the reason why there is a deaerator, and you have also the reason why this flow is small. It's because it is in the gas phase. Okay, questions about this? No? Okay. Next question then. So where is the equation for CP3 in the diluter derived form? And the idea is the following: is that when you have, so the diluter is the mix of the beer and the water. Okay, so the difference between the beer and the water is the alcohol that is in the beer flow. It's not a huge amount, so it's mainly water and a small amount of alcohol, and you would like just to add a little bit more water in it. Okay, and the idea of the of making the calculation is just to consider that in the liquid phase you can sum up the CP of the different compounds that are in the mixture. This is a general assumption that is always valid, except if there are high physical interactions between the compounds in the mixture. So if the fruit, for example, reacts, or if you have big electrolytes. So if if when you add water in a mixture that it has to separate with the ions, then there will be what we name an enthalpy of mixing. Okay, but in the case of like the water when you are, that you add in the beer flow, then you can make the sum of the CP. Okay, and as soon as you know the CP of water, as soon as you know that the flow of beer is not going to be affected, so the flow of alcohol is not going to be affected, by using the temperatures that you receive, you will be able to identify the value of the CP of the beer. Okay, and therefore, as soon as you know the CP of the alcohol compared to the CP of water, you can play with the same principle everywhere by summing up the flow of alcohol and the flow of water. Okay, and this is valid, of course, if you remain in the gas in the liquid phase. As soon as one of the two compounds go in the gas phase, then the problematic becomes a little bit more complicated in the calculations. Okay. Right. Questions about this? It's clear as well? Okay. So the question about the deaerator is already made, and of course the assumption is that the system is going to be reaching the ebullition. So it means that we have to give a set point of the liquid to be just at the pressure of the evaporation in the deaerator, so that you are sure that all the gases will leave the system. The next question, what is the most efficient way to solve a system of 5 nonlinear equations? Okay, I have two answers to this. The first one is, you will see the one who will attend my lecture in the next semester will know how to do this kind of solutions of 5 nonlinear equations with 5 unknowns. Okay, this is one way of giving you the answer. The other way is to be smart. In fact, in our case, typically we are working with flows, so mass flows and temperatures, which are related to enthalpies, right? When we write the equations of the mass and the energy balance, typically we are able to identify a sequence of resolution. So it means that we are able to identify an equation that has only one unknown, and then knowing this one, then the unknown is going to enter into the next equation, where we were having the two unknowns, in which one has been calculated by the first equation. Okay, so by doing this, it's possible, and in your case, in the exercise, it's always possible to do a reasoning that allows to say, I'm going to solve this equation because I know this, and I will be able to calculate this variable. Knowing this unknown, then it is known, and then I'm solving this equation, I can calculate the next one, etc. Okay, so it means that the answer for solving a set of nonlinear equations, most of the time, you can do it by defining the right sequence. Now, if it happens that you are not able to find, to associate one equation and one variable because something is missing, then the trick will be to make a guess. So you will guess one of the value, then you fix the value, and if this equation now has, if the next equation that had two unknowns has one that is fixed, then you can calculate the other one and then progress in the sequence. But there will be a point where you will see that the last variable will be you will calculate the value that you have guessed in the beginning. Okay, and in this case, you will take this value and you will have to do a solving procedure. If you have MATLAB, for example, you will use fsolve. If you are working with Excel, it's a goal seeker as well. Okay, so this is my answer. Of course, you can always do this principle and try to solve a set of equations in a simultaneous way, but typically in our case, I would say that normally you can find a sequence of resolution. Okay, mainly because the mass balance are linear, so it means that they are quite easy to solve. And to see who is calculating what. And the energy balance are, in our case, most of the time, bilinear. So it means that you have the incidence of the flow rate and then the incidence of the temperature. Okay, and typically, it's quite easy to say that if I have this, then I can calculate this. Okay, and now the people who have asked the question can ask the assistant if they have not identified the sequence, or myself. Okay? Right, and the last question before. And yeah, there was a question concerning the question of the valves, and it seems that there was a typo in the correction, so it's easy to answer, right? Okay, so now I would like nevertheless to add a little bit of additional information on what we are doing when we look at this okay, so something that I wanted also to highlight in the mass and energy balance that you have to write is the fact that you have different networks that have to be identified with, and networks are connections of pipes that link flows that have the same composition. An example of this is given here in the ammonia cycle, where you will see that you have, on the one hand, a flow of water that is coming here and that is going to go there. So it's the same flow with a given composition, which is water. You have another flow, which is in this cycle here, which goes via the heat exchanger here, then the valve, and then afterwards the other heat exchanger before entering the compressor. Okay. In this case, it's the ammonia that is the working fluid. And what is happening, in fact, when we do this representation, in reality, the ammonia is inside the tube, for example, and the water is indeed entering here and is separated from, so we'll do a contact current, so the water is going in this direction, and it is separated from the other flow. So it means that there will be no mixing between the ammonia, that is the ammonia here, and the water, which is here. Okay, and then if I'm looking at what is going to happen later on, so in this other heat exchanger here, you have the glycolic water, which is passing through the heat exchangers here, and is transferred here, is going to do this work, this flow here. So normally we should have added a small pump here, which allows the glycolic water to circulate. And there will be a next subsystem here, which is the process water that is going to pass through to the other side of the heat exchanger. Okay, so when we do this, it's important because it means that at the level of the heat exchanger here, again, if I'm using the temperature enthalpy diagram that we will plot a lot in this course, so what you will see is that you have, I'm taking the one with ammonia, for example, and glycolic water. The ammonia is going to, in this case, evaporate, so it will go at constant temperature like this, while the flow of glycolic water will come back at -1 here, -1, and will be cooled down to reach the same heat load at -5. Okay, and the heat load is the amount of heat that is delivered by the glycolic water is used to evaporate the ammonia. Okay, so it's important to do this analysis because it allows to identify the heat that is exchanged in every one of the operation. Okay. A special case is the case that I would like to discuss now, which is what is happening inside the boiler. So the boiler is going to be defined by this subsystem here, where you have the fuel that is entered. So this is the fuel. This is the air that is used in order to burn the fuel. This is going to be merged and do what we have modeled here by a flame, which is the combustion. And the combustion is going to create gases, hot gases, that will then be cooled down in order to heat the steam that is here, so that goes from the liquid to the gas, to the vapor state here. Okay, so there will be here an interface, which is a tube in which heat from the gases will be supplied, and we will name it the heat of the boiler, that will be supplied by cooling down the combustion gases to the temperature of at the chimney, which is measured here with two important information. On the one hand, the temperature at which the gases have been cooled down, and the oxygen content, which is the amount of excess oxygen that we have added into the combustion. And there was an additional information that was given here, which was the adiabatic temperature of combustion, which is the temperature at which the gases are before they start to exchange. So this is a temperature that never exists, but this is the temperature that the gases would have if the energy of the combustion would not be exchanged outside. The problem is that as soon as combustion starts, there are some radiation that starts as well, and the temperature is therefore decreasing because the flow is delivering some heat. Okay, so I'm going to explain you a little bit more in detail what is happening inside this the boiler and the combustion. Let's find my mouse, okay, and let's then go here. Okay, so when we look at the boiler, we see that we have fuel that is entering, oxygen that is entering, and flue gases that are leaving the system. So the first thing that we will have to do when we will do the system analysis and we will understand what is happening inside the process is to characterize what is defined as being the fuel. And typically, what we will obtain from the analysis about the type of fuel that we have is the chemical composition. So we will know what are the molecules which are in the fuel and the atoms that are concerned. Typically, we will also need something which is named the oxygen requirement. So I would like to know how much oxygen, which means how much air, I have to use for realizing the combustion. The other information that I will need is, of course, how much I will have to pay for each unit of fuel that I will buy. And this amount is given in different units. So typically when you have a natural gas, it will be per cubic meter. The oil will be per liter, okay? And the wood will be per kilogram, for example, or ster in French, okay? Another thing that is also quite important to know is the availability of the fuel that we will use in the boilers. We have to be sure that the fuel will be there when we will need to produce, to distribute the, to operate the boiler. And this will be also very important when you will have to decide which kind of fuel you use in a boiler. So if, for example, you have a gas grid that delivers gas in your facility, then it will be much easier. Another important information that we will need is the energy content of the fuel, and I'm going to explain what it means. So let's start with the composition. So typically, a fuel has a composition which is not necessarily described in a collection of molecules, because oil, for example, is a huge collection of a lot of different molecules. So typically, the first thing that we'll look at is the ultimate composition, which is the amount of atoms that we have in the mixture. Typically, we will have carbon and hydrogen, which are the hydrocarbon dimension, which is typically what we have when we buy oil or gas. Okay, so some atoms of carbon, some atoms of hydrogen, and then some smaller compounds. So for example, we can have nitrogen coming with methane. Okay, so there will be nitrogen. Sometimes you will have also sulfur in the mixture. Hopefully not too much, but in a gas, for example, in natural gas, you will have some sulfur in it, mainly because it is used in order to give an odor to the gas, so that you can smell it. Okay, and if you can smell it, then you will identify if there is a leakage. Okay, and it means that this sulfur is added in the mixture. And sometimes there will be also some amount of oxygen. So, for example, if you want to burn methanol or ethanol, there is oxygen as well in the mixture. So typically we are talking about molecules, but in fact I'm talking about moles, which is a huge number of very small molecules, okay? 10 to the power 23, okay? And it's a universal constant, okay? So which allows me to speak about the weight of a mole, okay? And then that's what is named the molecular weight. So it means that now I can tell you that as soon as I have 1 mole of carbon, I will have a weight of 12, etc. For the hydrogen is 1, for the nitrogen is 14, and for the oxygen is 16. Okay? Now, when we do a combustion, there are a lot of things that has to happen. So I'm taking the molecule of fuel. I'm going to add some oxygen to it. Okay? But, okay, this table can burn. Okay? But you can see that with oxygen around and with the fuel that is here, nothing is happening. Okay, the same for the wood that you see in the forest. The wood is not going to burn. Okay. However, as soon as you ignite, so it means that you give the energy of activation, then the processes of combustion is going to start. The molecules will start to break, and they will start to deliver the heat, the energy that was in fact stored in the formation of the molecule. Okay, and this is the principle of the combustion. And it means that, and the fact that the molecules do break into atoms first, and the fact that it delivers heat means that it delivers the energy of activation for all the other molecules. Okay, which then creates a chain reaction. So as soon as we have a little bit of ignition, then the processes of combustion starts, and you have an explosion. So that's what is happening in the internal combustion engines. Okay. Now, knowing the composition of the fuel, I can directly calculate the amount of oxygen that I need, because each time I'm taking one of the molecule out of the system. I should use this because then it will be easier for. So each time I have one molecule of or 1 mole of carbon that is liberated, it will need 1 molecule of oxygen to create the result of the oxidation, which is the carbon dioxide. So it means that each time I have a mole, and I'm talking about moles and not kilograms for the mechanical engineers, right? So chemical engineers know from the beginning that a chemical reactions is always measured in moles, and that's the molecules or the atoms that are not lost, okay, in chemical reactions. So we have to speak about moles, right? So each time we have 1 mole of carbon, then we need 1 mole of oxygen to make carbon dioxide. So 2 things, I need oxygen and I create a new molecule, which is a gas molecule, which is here. Each time I see a hydrogen, I need 1/4 of a molecule of oxygen in order to make half of a molecule of water. Each time I see the S, I will have to combine it with the same amount of oxygen to make the SO2, which is one of the possible substance that results from the combustion. Okay, and what we can also say is that the N2 is going to is a priori neutral, but if you have a nitrogen inside the molecules, they will recombine and form nitrogen. Okay, so which means that by making the sum of what I need in form of oxygen, if I know the composition of the fuel here, I know how much moles of oxygen have to enter the system. Okay. Now I told you that I need ignition, and I need oxygen and fuel. That means that they have to meet together, and this is what is happening in the burner. So in the burner, the oxygen is going to react with the combustion, with the fuel to make combustion, which means that I will have to calculate, in fact, not only the amount of oxygen that I need, and each time I'm having the oxygen, then I have also to add the fact that the nitrogen is going to come if I'm using air as an oxidant, okay? And I will add something which is named the air excess, which is the amount of additional oxygen that I will add in the burner to be sure that the combustion is complete. Okay, it's just a question of increasing the probability that a fuel meets an oxygen molecule. Okay, the better the burner, the lower the air excess has to be. Okay, but if you do not have a very nice mixer at the level of the burner, then there is a risk of not doing the complete combustion, and therefore the people do typically add a small amount of oxygen to be sure that the combustion will be complete. And when the combustion is complete, then you can calculate what will be the resulting flow in the combustion gases. So I will have the production of carbon dioxide, the production of water, the production of solid sulfur oxide, plus the nitrogen that will have that has not reacted, perhaps it has been created a little bit from coming from the fuel here, and plus the excess of oxygen that is not used by the combustion. Okay, by doing this, I have the composition of the gases, right? With an important element, which is the carbon dioxide, that is typically creating the global warming. Okay, so the global warming is mainly coming from the fact that this carbon was, in fact, harvested in the Earth 100 million years ago. Okay, and is released today in the atmosphere. Okay, if now the fuel is wood, then this burden does not exist because the carbon is coming from the atmosphere and has been harvested by the biomass. So what is happening when we break the molecule is that we deliver a certain amount of heat. And this amount of heat is, in fact, the release of the heat of the energy of formation of the molecules of fuel. Okay, so the molecules have been created hundreds or millions of years ago. They include a certain amount of energy, and when we do the combustion, we liberate this amount of energy, which is the energy of combustion. And if this amount of heat that is released, which is the difference between the enthalpy of formation of the products and the enthalpy of formation of the reactants, this amount of heat is going to heat the fumes, which are here. And when the fumes are heated, if nothing else is happening due to the first principle of thermodynamics, then we will have the fumes will be heated and will reach a temperature which is the adiabatic, named the adiabatic temperature of combustion. Okay, the amount of heat. So when the gas reach this temperature, they will be really hot, and they will be there then ready to deliver heat to whatever things that are at lower temperature. Okay, and that's what is going to happen in a boiler. The maximum amount of heat that can be harvested by cooling down the hot gases to the lowest possible temperature is named the heating value. And the heating value is defined and needs a definition of what is the lowest temperature. And by convention, this is 25 degrees C and 1 bar. And here I have to say that there are some assumptions behind, because the problem is related to the presence of water. The water that is created during the combustion is going to be in a gas phase. It will therefore be cooled down, but at a certain temperature, depending on the concentration of water, it will start to condense and go in the liquid phase. Okay? The temperature at which it starts condensing is around 50 to 60 degrees C, depending on the concentration. But it means that when I'm cooling down the hot gases, at a certain time, the water is going to go into the liquid phase and will deliver the heat of vaporization. In most of the boilers, especially in the industrial boilers, we do not like, or we don't find very interesting to condense the water, because typically we are not going to cool down the combustion gases to this low temperature. Okay, which means that most of the, especially in Europe, most of the people who are selling energy are defining the amount of energy in the form of the lower heating value. The lower heating value is the amount of heat that can be harvested by cooling down the gases up to 25 degrees C without trying to condense, without condensing the water that is formed during the combustion. And the higher heating value is the same value, but by making the assumption that the whole amount of water will be condensed. Okay? So, which means that the difference between the higher and the lower heating value is the water condensation. And it depends on the amount of water that has been created during the combustion. Okay? The higher heating value, even if I'm cooling down the hot gases up to 25 degrees C, will not be easy to attain, because the water will still have a partial pressure and will never completely condense. The only condition is that we have to start with a saturated air in humidity, which is most of the time never the case. Okay, the higher heating value is the lower heating value is smaller than the real value that we can get out of a condensing boiler, because the condensing boiler will start to condense. With one big condition, it has to reach very low temperature. Okay. Now it means that I have the higher heating value, which is defined by cooling down the gases that have been heated by the heat of combustion to this adiabatic temperature of combustion, and that will be cooled down up to the 25 degrees C, which defines the lower heating value of the fuel. The reality is that we will not cool down up to a certain temperature. We will stop at standard temperature, so we will stop at the temperature which is the temperature of the chimney. And there is a trick in order to calculate the amount of heat that can be released by assuming that this is a straight line. So it means that if the Cp is a constant, so this is the slope is the Cp, which means that by knowing the lower heating value, I can calculate what is the amount from there to there that will be lost as a function of the temperature at which we are. So the lower heating value is, the lower, no, that's not what I wanted to show. So the lower heating value is a characteristic of any fuel. You can have simple fuels or mixtures, like what I have shown just here, which is the composition of the natural gas, which is a mixture in reality. It's not pure methane. Okay, and so this gives you, for example, the composition at the level of the gas grid. And when you have to calculate the heating value of a mixture, you make just the sum of the heat of formation of each one of the compound, and of course it is weighted by the amount of molecules that you have in the mixture. And lower heating value does not only concern the typical gases like this, but it concerns also different types of fuels, which can also be waste. So it means that you can also define a lower heating value for vegetable waste, pig manures, or wine, etc. Okay, everything that can be burned has a lower heating value. So when now we do the combustion, then we have to do the heat exchange, okay? And I just give you some pictures about what it means having doing the heat exchange. So this is the interns of a very big boiler. So you can see that there are a lot of tubes that are the tubes of the water that will be produced and transformed into steam, okay? And that will see burners here, okay? So it means that boilers, and so the hole that is here is also here, and the burner will show the flame to a collection of tubes like the one that are seen here, okay? And then the flow will continue and go through the whole list of tubes here to finally leave the system at the chimney. So this is another representation here. So the fumes will go from here where you have the burner up to, by traveling up to here where you have the chimney. Okay, so it means that the heat of the lower heating value will not be so easy to extract. There will be, on the one hand, the fact that the air can be hotter or lower than the lower heating value, and it will bring you some more energy in the system. You will have losses at the level of the envelope of the boiler, and typically we say that there are 2% that will be lost by just the fact that the boiler is going to heat the surrounding by radiation. Then you will have the real amount that is harvested, and then the rest, which is then lost in the chimney, which is the amount of heat that is released in the environment, okay, in form of hot gases. So you have in the exercise a temperature here which is 200 degrees C. You have to consider that you will lose part of the heat load here. And what you can see is that if you want to calculate exactly what is still available here, everything depends on the MCP of the combustion gases. And this MCP can be approximated, as I have already said, by if we know the adiabatic temperature of combustion, and if we assume that instead of having something which is nonlinear we have something which is linear. Which means at the end that you will have to calculate where you lose the energy that you buy in the boiler. There will be part which will come from the radiation losses and part that are the combustion gases that leave the system. And therefore you will be able to calculate what is the useful heat that is delivered, which is the heat that is coming from the fuel, including the lower heating value plus the difference between the sensible heat available in the fuel as a function of the temperature at which the fuel is delivered, plus the amount of heat coming from the air, which is the flow of air that is calculated to burn the fuel, times the temperature difference between the adiabatic temperature, the reference temperature of the air and the real temperature of the air, and from which you have to deduce the amount of losses in the system, the combustion gases and the radiation, which will then allow you to know what is the efficiency of the boiler, which is the ratio between what you have obtained, which is or bought, which is the fuel and the air, the content of energy of the fuel and the air, and the heat that is effectively delivered by the boiler. And this one can also be calculated as a function of the losses that we have identified above. And the last dimension is that when we calculate the carbon dioxide emissions, so we have calculated how much carbon dioxide emission is delivered for one unit of fuel that is burned. Okay, this is coming from the stoichiometric equation of the combustion. But to this one, we have to add what we name the life cycle of the fuel, which is the amount of emissions that will be done due to the fact that we have to extract the oil, that we have to process and transport the oil and deliver to the place where you are using. And believe me or not, but from 15 to 40% of the carbon dioxide emissions of oil are emitted before the oil is entering the boiler. Okay, so it's a huge amount. Okay, and it depends on the type of fuel. So here I give you some values. So for the diesel, gasoline, and natural gas. So what you can see is that in the case of natural gas, is 19% is delivered before being arriving in the plant, and for the gasoline and the diesel is around 20 in this case. So it's very important to consider this, because even if you have renewable fuels like the one here, so the wood, you will still have some carbon dioxide emissions that is due to the fact that you have to transport the fuel. Okay? Do you have questions about combustion? It's clearer now? Okay, then we make a break, and in 15 minutes I'm going to start with the next step, which is the exergy analysis.